In the last class, we have little bit discussion about the cannizzaro reactions. Let's extend the discussion a bit further. So, in the last class, we basically focused about the rate of the cannizzaro reaction by taking the simple formaldehyde molecules. Now, takes two type of molecule. One is the formaldehyde, and the other is the benzaldehyde. Okay, so this reaction takes place between the two types of aldehydes. Both of them have no alpha hydrogens. So is this reaction taking place between the two types of aldehyde, we can say that this is the crossed cannizzaro reactions. We can say this is crossed cannizzaro reactions. Now we are using concentrated base. So now the point is that in the first step, the OH minus attacks some of the carbonyl centers. So obviously this carbon, now we have to decide which carbonyl center is more electron deficient and which is comparatively rich. So if you will see, when this carbonyl group is attached with an benzyl group, so there is some kind of resonance is taking place. So this carbon center is somewhat more electron rich than this formaldehydes, because this it is not supported with any kind of plus M group. Like here it acts as a type of plus M group and participate in case for resonance. So somewhat the electron deficiency is here compensated by the electron donating group, but here it is more electron deficient. The conclusion is that now this OH minus, will attack here. Okay, so what will be the forms? Now HCO minus, Na plus, and H here OH minus. That means it will form the salt of carboxylic acid and it is reduced. What will happen? This is benzyl alcohol. So from this, what we can say, out of these two kind of aldehyde, this is more electron rich, comparatively more electron rich this formaldehydes. So that's why this benzaldehyde become alcohols. Okay, that means it is reduced. So it is reduced. So we can say one term, electron rich. Electron rich means reduced. RR. Electron rich means reduced. Okay, so whenever we combine it with two types of aldehyde, we will see the more electron rich aldehyde which will be reduced. Okay, so now little bit discuss about the reactivity. So we can say the reactivity of this aldehyde. So what will happen is formaldehyde will be more reactive than, if some electron releasing group, it will then less reactive than formaldehyde, and here will be like that. So it will follow like this kind of trend, because it is more electron deficient, it is more prone for the attacking of the OH minus. So this is the reactivity order. This is more electron deficient. For the enhancement of this reaction, we first of all we need the very electron deficient center, then only the redetermining step RDS, shift of hydrates, can take place. Okay, so this is the crossed cannizzaro reaction. Now we will extend the discussions towards the intramolecular cannizzaro reactions. Okay, so let's take here this is one aldehyde and this is one aldehyde. So out of these two aldehyde, obviously in one of the centers the attacking of this OH express, so one will be reduced and other will be oxidized. One will be reduced and other will be oxidized. So this is called intramolecular cannizzaro reactions. Okay, but sometimes we are confused which is more electron center and electron rich and which is more electron deficient. Let's take a very interesting example. Okay, so this is one aldehyde. Okay, now we have to decide which aldehyde is more electron deficient, okay, and which is more electron rich. If we'll try to see the resonating structures, if you'll try to see the electron resonating structure, you will find like that. So this aldehyde is undergoing resonance due to the presence of lone pair of the oxygens. So this electron deficiency is somewhat compensated due to the resonance presence over the lone pair over the oxygens. So the conclusion is that, yeah, here this aldehyde, this is more electron rich and this is very electron deficient, and previously we have our conclusion is that this electron rich means it is reduced. So this is electron rich due to the resonance effect. So this electron rich, that means it will be reduced. So we can easily write the product. We can easily write the product. So the product will be, it will be reduced and it will be oxidized. Okay, now let's take a very interesting example. Okay, let's take a very interesting example. Now here one aldehyde group is there, here one aldehyde group is there, and here one aldehyde group is there, here one aldehyde group is there. Okay, now what will happen? Obviously, if you will see very minutely the mechanism of the cannizzaro reactions, once the hydroxyl ion attacks the electron deficient center, the next step is the hydrate shifts. So definitely the hydrate shift will be more comfortable when both the aldehyde group will be very little bit adjacent. I am saying comfortable, that I am not saying possible impossible. So it is a little bit comfortable if both the aldehyde groups are adjacent to each other. So out of these two aldehyde, one will be reduced, one other will be oxidized. So let's write the oxidized and reduced product. Okay, now we have to decide out of these two aldehyde which is more electron enriched and which is more electron deficient. You can think here it kind of hyperconjugation taking place. This comes here, this comes here, and this comes here, and this comes here, and this comes here. Are you getting my point? So with reference to this alcohol group, this aldehyde which is at a para position, it is somewhat stabilized by the resonance. It's a kind of getting electron flow from this hyperconjugation effect. So this center become more electron rich. Electron rich means it will be reduced, and electron deficient means it will be oxidized. So on this basis we can write the product here. So this is alcohol and this is sodium salt of carboxylic acid, and this is what is electron rich. Electron rich means it is reduced and it is electron deficient. It will be so. This is our final product in these reactions. Let's take one more last example. This is naphthalene. This is naphthalene. Okay, here I am putting two aldehyde group. So now what will happen? We know the alpha position is more electron enriched. Okay, the alpha position is now more electron enriched, so obviously it will be reduced and the other will be oxidized. Okay, because for this case we can see, if we will show the substitution reactions, electrophilic substitution reaction, then what will be the resonance hybrid? Okay, suppose in the place 1 I am showing the substitution reactions, and same case if I am showing the substitutions reaction in the place 2, that means beta position. Now the structure will be alpha beta. Okay, and you see here you can draw one more resonance structure, but here now we are not able to draw the resonance structures because it's not undergo conjugations. So electrophilic substitutions reactions, then this need electron lobbings, so it will be getting electrons from this position in a more favorable way than this beta positions. Are you getting my point? This is electrophile needs electron loving. Okay, electron loving, so this position is prompting electron is a more comfortable way than this beta positions. So we can say, if you are getting prompting of electrons from this alpha position is more easier, so you can say the alpha position is more electron enriched. Alpha position is more electron enriched, so this aldehyde is somewhat more electron enriched than this beta positions. So electron rich, that means reduced, so this aldehyde will be reduced and this aldehyde will be oxidized. Okay, that's all about the cannizzaro reactions. For instance, I can take one more example. Suppose if two carbonyl groups are present adjacent to each other, uh, this will not undergo in cannizzaro reactions, because cannizzaro reaction is only for aldehyde, not for ketone. Okay, here hydrate shift will not be taking place. Okay, so here cannizzaro reaction not possible. I am writing the molecules again in a clear manner. This is the molecule. I am saying about this molecule. Here no cannizzaro reaction can take place. Okay, that's all.